Here we'll look at using the limiting reactant to find the quantity of a product. And so we said that the amount of product formed is dependent on the limiting reactant. In this case, we're going to form copper sulfide. But if I run out of copper, then obviously I can't form any more copper sulfide. If I run out of sulfur, I can't form any more copper sulfide. Even though there may be one reactant that you have extra of, there's some left over. But if you run out of one reactant, then that limits or determines how much product can be formed. So the difference between some of these limiting reactant problems and just some of the general mass stoichiometry that we've done in the past is that now they're going to give me both masses. They give me masses of both reactants. And I have to figure out with those masses, do I have a 2-to-1 ratio of moles like this balanced equation? I'm supposed to have 2 moles of copper for every 1 mole of sulfur, or some kind of a comparable 2-to-1 ratio of moles. If I don't have the 2-to-1 ratio, then is there one reactant that's going to run out first? And then that limiting reactant is the one that I'll use to determine how much product is formed. So if I flip back like a page or so, they gave us this same initial problem, 80 grams of copper, 25 grams of sulfur, and earlier it just said determine the limiting reactant. And we said, well, okay, I want to use that 2-to-1 ratio from the balanced equation, but that's a mole ratio. And so our first step was to get those grams converted to moles for each reactant. So I have to do it twice. Then we said choose one reactant. It doesn't matter which. Choose one of the reactants and use that mole ratio from the balanced equation to figure out moles of the other reactant needed to completely react with all of the reactant that you chose. So in this example, what if we chose the copper? So we have 1.26 moles of copper. So then how much sulfur would I need if I want to completely react the copper? So this is just that little mole to mole switch, super easy, painless, right? And so the key is that these amounts that we initially calculated, that is what you have. And now here when I'm comparing the two reactants, I'm calculating the amount that I need. So I needed 0.63 moles of sulfur. So then you compare that to the amount of sulfur that you have. And at that point then we said that we actually have extra. I only need 0.63 moles of sulfur, but I have 0.779 moles. So I have a little extra. So we said then that sulfur was the excess reactant. And so by process of elimination, if you found the excess, then the other reactant is limiting. The copper was our limiting reactant. Well, the idea then is that the limiting reactant, the copper, is going to run out first. And so when I run out of copper, I can't make any more copper sulfide. So the amount of product is dependent on the limiting reactant. And then sulfur was the excess. So it is not dependent on the excess. There will be excess sulfur, which is fine. But when I run out of copper, the reaction will stop. Okay, so now this part becomes pretty simple. Earlier, we already calculated this number here. We already calculated moles of that copper. All we did was take the original mass, 80 grams, and then convert that to moles using the molar mass on the periodic table. Well, since you already have it in moles, you can take a little bit of a shortcut with your stoichiometry. I need moles anyway so that I can convert between copper and copper sulfide. To go back and use that 1.26 moles already calculated, it would have been set up as that 80.0 grams. But we didn't want it in grams, we needed it in moles. The periodic table tells me about 63.55 grams for every 1 mole. That's where I get the 1.26 moles of copper. But yeah, since we had already calculated that so we could determine the limiting reactant, just start right away with your moles of copper, because then you can use the ratio from the balanced equation right away. You can use that 2 moles of copper for every 1 mole of copper sulfide. So when I first set it up then, I want to cancel moles of copper and switch it to anything I want. In this case, it's the copper sulfide. From there, I want the final copper sulfide back in grams. So then I can cancel moles and put it into grams. And this 159, that would be off your periodic table. Just add it up. Then we multiply any numbers on the top, divide by anyone on the bottom, and bingo, we're all done. Now, they wrote the answer in scientific notation, which is fine, but it could also be written as like 100 grams. And so the idea is just that we have to figure out which reactant is limiting, because that's the one we'll use to determine the amount of product formed. When I run out of one of the reactants, then I can't make any more product. This is a really typical problem, kind of combined with that earlier limiting reactant step, and that usually we measure the amount of each reactant in grams, so we have to convert them to moles. Then we can do all the stoichiometry using the ratios in the balanced equation. But again, at the end, I probably want to measure my final product back in grams. Now, they do give us one other little sample question, and it looks really similar to, I believe it's maybe like question 23 in the book. Oh, let's see here. Yeah, these are really similar. So it's the same reaction as earlier. It's this combustion of ethene, and we have 2.70 moles of the ethene, C2H4, reacted with 6.3 moles of oxygen. They gave me a little shortcut here in that it's already in moles. Usually it would be grams, and I'd have to convert it to moles. I'll take the shortcut. So before I can calculate an amount of product formed, I would need to know, well, is the amount of water formed dependent on running out of C2H2 or running out of oxygen? And so again, just to review, if they're both in moles, you can pick moles of either reactant. It doesn't matter which you start with. Let's say I start with this guy because it comes first. And then you just do a quick little mole to mole switch, cancel moles of the reactant that you chose, and then switch it to moles of the opposite reactant. And then we just plug in the ratio from the balanced equation. So I'm going to plug in 1 to 2. Okay, and so now we convert this then from moles of the C2H4, 2.7 times 2, over to moles of oxygen. And we got 5.4 moles of O2 oxygen. Now, the conversions themselves, the calculations, those are all really simple. I think it's now like understanding, what do these numbers mean? Well, these amounts up here that were given to us, these are the amounts that you have. What I calculated here, this is the amount of oxygen that I need. And now we just compare. I need 5.4 moles of oxygen. I have 6.3. So I actually have a little bit of extra oxygen. So oxygen is my excess reactant. Well, then by process of elimination, the C2H2 must be the limiting. I found the excess, the other one's limiting. Now, if you would have done this in the other order, let's say you would have chosen the 6.30 moles of oxygen to start with. Now, you don't have to do both, but if you did, you would say, all right, let's cancel moles of oxygen and switch it to moles of the other reactant. We're trying to determine the limiting reactant or reagent. I plug in the ratio, 1 to 2, and we throw it in our calculator. And I'd be looking at about 3.15, right? Moles of the C2H4. That then, what I just calculated, is the amount that I need. If I wanted to react all of the oxygen, I need a little more than 3 moles of the C2H4. Well, then same thing, we'd go back and compare it to the amount that I have, and then we'd say, ugh, I don't have that much. So if you don't have enough, then you found the limiting reactant. And by process of elimination, the oxygen would have been in excess. So all of that is done so that we can finally figure out how much water is produced. So the amount of water formed is dependent on the limiting reactant. I can't make any more H2O if I run out of the reactant that includes the hydrogen. This is my limiting, and this was my excess. So it's the limiting reactant, woo, lots of arrows, that'll determine how much product is formed. Now this one is just having us keep everything in moles, which is kind of handy, I guess. So that now I can take moles of the limiting reactant, and we have to go back to the amount that we have. So the limiting reactant is going to be this 2.7 moles of the C2H4. That's what I have. I needed 3.15, but I didn't really have that. And so we go back to the amount of limiting that we have, and then we can use the ratio in the balanced equation. So I'll cancel moles of C2H4 and switch it over to moles of the desired product, which in this case is water. There's 2 moles of water for every 1 mole of C2H4. And then we're good to go. All right, so 2.7 times 2 is 5.4. And this would be moles of water. There we go. Moles of water produced. And here we can just keep it in moles. Typically, I might go then back to grams if I were actually going to measure the amount of water formed. So then maybe I would tack on one more little conversion and switch this 5.4 moles of water back to grams of water. But the key is that before I can convert between any reactants and products, I need to know which reactant is going to run out. So we do this first little limiting reactant step so I know which reactant I should start with when I do my final conversion to determine how much product is formed.